Today I am going to solve one numerical example to verify of first law of thermodynamics. Here is the problem statement. Initial and final state of a gas is as follows. Initial state P1 is 100 kilopascal, V1 is 1 meter cube, T1 is 300 Kelvin. Final state P2 is 100 kilopascal, V2 is 2 meter cube and T2 600 Kelvin. The process is at constant pressure, so P1 is equal to P2 is equal to 100 kilopascal. Check if the first law of thermodynamics is followed. So del U is equal to Q minus W. So by calculating change in internal energy del U, work done by the gas W and heat added to the system. So by calculating change in internal energy and work done by the gas, we can and heat added to the system, we can verify the first law of thermodynamics. Now here that given data, we already talked about that things. Now first step number 1, calculate the number of moles N. So from the ideal gas law, to find N, to find the number of moles, we use ideal gas law. PV is equal to nRT. So using the initial state P1 V1 by RT1, so P1 is 100 into 10 to the power 3, then V1 is 1 meter cube, R is 8.314 and T1 is 300. So from that, if I do the calculation, so we'll get N is nothing but 40.11 mole. So number of moles of the gas is N, that is 40.11 mole. Next is calculate the change in internal energy del U. So the change in internal energy del U is given by del U is equal to NCV delta T, where CV is equal to 3 by 2 R for a monoatomic ideal gas. So substituting the value, so del U is equal to 40.11 into 3 by 2 into 8.314 into 600 minus 300, means T2 minus T1. So del U we can calculate. So del U is nothing but 150086 joule. So that is 150.09 kilojoule. Now change in internal energy is del U is equal to 150.09 kilojoule. So here we got the internal energy change. So next step 3, calculate work done by the gas W. So work done by the gas during an isobaric process, because P is constant, that is given by P is equal to P into del V. So P V2 minus V1. So substituting the value, so P is 100 kilopascal, 100 into 10 to the power 3 into V2 2 minus 1. So that is 100 kilojoule. So work done by the gas is W 100 kilojoule. So now we have internal energy change and work done by the gas W. Now first law of thermodynamics. So we know, according to the first law of thermodynamics, Q is equal to del U plus W. So substituting the value del U, so here del U is nothing but Q minus W. So Q will be nothing but del U plus W. So now substituting the value del U and W, so that is 150.09 kilojoule plus 100 kilojoule. So this is internal energy change and this is work done. So Q is 250.09 kilojoule. So the heat added to the system is Q 250.09 kilojoule. Now another way we can calculate that heat added. So heat added in isobaric process, we know that is given by Q is equal to NCP delta T. So we got from the first law of thermodynamics that heat added is 250.09 kilojoule, and now we know for the isobaric process that Q we can easily get NCP delta T. So here Cp is nothing but 5 by 2 R. Now substituting the value, so Q is nothing but N 40.11, then Cp value 5 by 2 into R, so that is 20.785. We can do that 40.11 into 8.314. So that is 20.785. Then T2 minus T1. T2 minus T1. So if I do the calculation, so finally we will get 250.16 kilojoule. So the heat added to the system Q is 250.16 kilojoule. So now earlier we have the 250.09 kilojoule. Now here by using isobaric process we got 250.16 kilojoule. So that is nearly equal to the other way calculation of the Q heat added to the system. So now summary of the result. The data follows the first law of thermodynamics. Del U is equal to Q minus W. So we calculate del U, that is 150.09 kilojoule, and W work done, so that is 100 kilojoule, and heat added to the system, that is 250.09 kilojoule. Okay, so now if I plug that, so del U, that is 150.09, Q is 250.09, and then W 100. So it will verify the first law. And another way, we also Q we got 250.16, that is equal. So now we can say the conclusion, the first law is verified with given data. That's it. Thank you.